that, then I can factor A out. That didn't do it for you? Or I missed the question?
I just didn't think on. Can you like do it one more time, but like just a little slower?
But do it what?
A little slower.
All right, if I take, this what we really need is there, so they can get this out.
So you factor it to be M3 plus M5 times A and then divided by M3 plus M5?
Yes. That's what it did over there, squeezed it over there. All right, so if I have x plus y equals 4. If I add three to both sides, the math people say I'm good. They're happy with that. That if this is true, then this would be true. Do you accept that?
Yeah.
All right. Now, if instead I said, well, let's let z equal 3. So I'm going to add 3 to this side, but this side I'm just going to add z. It's same as 3. So I'm doing the same thing over there is I take this bit right here, that's equal to this. My second equation tells me that the tension equals that. So I just added this to the left-hand side, this to the right-hand side. So I added those and I added those.
Okay, yeah.
And the tensions cancel.
Yeah.
Remind me how the friction is 0.
I said in the problem that friction is 0. You mean how did I write it, or why
No,
is
I
it?
just why it turned to 0.
Because I said so. We're going to add friction into it. Alternatively, some people don't like this method. They'd rather do substitution. Since we have a value for tension, we could just plug this in for tension and have M3G minus M5A equals M3A. Add this to the other side to get, because we're ultimately starting to find A, so we need to get all the A terms on one side. And then that puts us exactly where we were before. It's one step longer, which to me, I don't want to do. There's also a question of at what point do you put numbers in. It's generally recommended don't put numbers in till the very end. However your mind is working at the moment, you have to do it. Some people will stick numbers in immediately. The advantage of sticking numbers in is, instead of writing M5, I'm actually writing 5 here, or instead of W3, I'm writing 3. It's easier to deal with. The downside is, if there's a part B to the problem, which requires just a small little tweak to the equations, then if you've been sticking numbers in all along, you might have to basically be starting from scratch. And we'll get into that as well. Questions before we take a little break? Let's take a break. All right, let's talk about friction, so that we can bring friction into the problem. All right, so if I've got a book, box, whatever, sliding on a surface, a table. If we zoom in on that, the surfaces aren't particularly smooth. And so at sort of a microscopic level, you've got these two surfaces that are basically fighting against each other. And we have two processes that are going on. One of them is sort of a puzzle piece, nook and cranny kind of look at it, so that I have two surfaces here and they're sort of interlocked, and so you have to get them out of the interlock in order to move. The other thing that's going on is as these two surfaces get close to each other, there's an attractive force between them. So we've got this, in essence, these tiny little micro normal forces as well as this attractive force between the atoms.
What do you mean by the attractive force?
It deals with the electrons being attracted from one side, being attracted to the nuclei on the other. That somehow,
Okay.
my understanding, somehow the symmetry gets broken so that you get one side that's more heavily negative and one side that's more heavily positive, and they get attracted. Now, the question is, when it starts to move, does anything change other than the fact that it's moving? There are two schools of thought. I will give you both schools of thought, and then I will talk about which one that almost everyone uses. So if I apply a force, if I push on this table right here, it's not moving. The bottom is not moving. There's friction that's keeping it in place, that is static friction because it's not sliding. I push more and more and more, the static friction is matching me. It's coming up, it's matching me until I hit a breaking point, at which point it'll start to slide. In one model, so if we did the friction force and the applied force, the friction matches, it keeps going like that. It's going to match me until it gets to that breaking point, and as soon as it hits the breaking point, it suddenly changes types of friction. This point right here would be the maximum static friction, and this right here is the kinetic friction, the friction of sliding, movement. The other school of thought is that if I have my applied force here, and I have my friction force, it's going to match me, it's going to match me, it's going to keep going until I hit a breaking point, at which point, once it starts to move, the kinetic friction is the same in this model. The kinetic friction is the same as the maximum static. Now, it seems like it would be very easy to actually do a test to determine which one is true. Trouble is, there are huge error bars on the experiments. And I tried to find someone who did a thorough investigation of this. I found someone who did a senior thesis on this, and basically there's just a whole lot of overlap between the coefficients. It's not easy to tell the difference. Now,
Why would anti-lock brakes be a thing if the second one is true?
that's a control issue. If the wheels don't lock up, you still have steering ability. And if they do lock up, you can't do much.
I thought it was an issue of the maximum static.
I've always been told it's a control issue. If you find differently,
Pretty
It'll be
sure,
illegal.
pretty sure.
You stop
From
sooner?
videos I've seen, you do stop shorter with the anti-lock.
it doesn't really feel that way, but it might.
It's not that different, but I'm pretty sure there is a difference.
Okay.
It's just something my high school physics teacher told me. I don't know if maybe he was wrong about that.
I'm telling you different lies. Okay. My high school physics teacher talked about, when someone's behind you and you can't see them, but you know they're there? He said that's that small gravitational pull between them. And when I was in graduate school, I asked one of the professors about that, and he said, I've never heard that before. And so, that force would be too small. You're sensing a whole lot of other stuff, body heat, muffling of sounds. So that was one of the lies he perpetuated. All right, so why don't we really know this better. My theory is friction is really an engineering problem, not really a physics problem. And engineers are practical people. A formula was developed in the late 1700s. It works. There's no reason really to investigate it much further. I know that there are some groups, there's a group at NC State who study this and trying to come up with something more fundamental. And I don't know if they've succeeded at this point or not. I suspect it's not going to be as simple as the models we're laying out today and that you'll see in most of what you work with as an engineer. I assume all of you are planning to be engineers? Anyone? I hesitate to ask this, any of you planning to be chemical engineers?
I wish.
You wish?
Yeah, there are actually girls in the chemistry program.
Oh. Okay. Yeah, I hadn't thought about it from that point of view, so. All right.
Got my priorities in order.
Now, in these two models, this model right here basically says that the friction is always going to be less than or equal to whatever this is, which is going to be mu times the normal force. In this model right here, it's mu, they're saying, if you look it up, if you type in coefficients of friction, static and kinetic, you'll come up with a chart. It'll give you two objects, two types of surfaces. It'll tell you the value of mu. And for mu sub s, it'll tell you mu sub k. Mu sub k is less than mu sub s. And then, but this model says that there's such huge error bars, you really can't differentiate. They're pretty much the same thing. This one, from what you look up, you'll find that mu sub s is less than, it's greater than mu sub k. And we have two formulas here, that the static friction is less than or equal to mu sy, and the kinetic friction equals u ky. This is, almost every physics textbook has this, but I don't know about the current textbook. The previous textbook had a page where they talked about this, but then potentially more and more, probably not in my lifetime, but more and more, it might shift, but just something potentially to keep an eye on. Now, most people consider that the heavier an object is, the more friction there is. Let's think about what that means. All right, so I'm going to push on this book. It slides, it stops. Why did it stop?
Friction.
Yes. Now, if I stick something heavy on it, just stick this on it, will it go as far?
No.
Has the weight of this thing I pushed changed?
Kind
What do you mean, kind of?
Well, it depends what the thing is.
of. Like talking about the whole thing?
I'm talking about what I pushed. The friction is between this and the table.
I mean, yeah, the weight changed. Because you put other stuff.
So this suddenly weighs more.
Oh, I meant like that weight plus what you put on it.
So what is that actually? Think about box on box. Oh, you weren't there for box on ground. The famous box on ground. What does a scale measure?
Normal.
Yes, scale measures normal force. What's happening, if you think about normal force in the interlocking model, I got this interlocking model like this. The more normal force, the more they are tightly pressed together, the more that the pieces are interlocked. Less normal force, they're not as pushed down in there. So the more normal force, the more that there is friction there. You're jamming the surfaces closer together. So it's the normal force, not the weight, that matters. Now, in a lot of situations, the weight's going to be equal to the normal force in magnitude. but that is not an assumption you should automatically go with. Since we're even going with this model, I would need to, in this problem, to tell you the coefficients of friction. So, between the box and table, or I guess we will call it a thing, use of S will make 0.2, use of K will make 0.1. When solving these problems, the first thing you need to do is establish, is it going to move? Well, sometimes I save time and I just say, assume it's already moving to start with. That way you don't have to worry about the static bit. But in this case, let's go through the whole thing. Let's assume that it starts at rest. In the substitution phase, we now have another substitution here, that this becomes the tension minus u sub sy equals m5a. So you first assume, have we exceeded the maximum static friction? Now the actual static friction, if it's not going to move, is just whatever it needs to stop it. But we work on the assumption, we plug in our maximum static here. And we work it out. In this particular problem, I know that this is y5. y5 is equal to m5g. I now take that and I plug it into there. So I have my two equations of tension minus us m5g is equal to m5a divided by, nope, not divided by, what am I doing there? Equal m5a, and then I've got m3g minus tension is equal to m3a. So basically I use the second equation to figure out what my normal force is going to be, plugged into that, and then I'm taking the first and third equation. I don't know tension, I don't know acceleration, but I have two equations, two unknowns, they're independent of each other. In other words, I can't derive one from the other. I now solve. Very similar to what we did before. I got m3g minus us m5g equals m5a plus m3a. Similar process did before. I added up the left-hand sides, added up the right-hand sides. Tension canceled out. And so we end up with acceleration is equal to m3g minus us m5g, I think, divided by m3 plus m5, right? Very similar to what I had before, other than I now have this friction term there. Let's plug and chug. 3 times 9.8 minus 0.2 times 5 times 9.8 divided by 3 plus 5. So I'll be kind enough to work that out.
That's 0.2, right?
Yes.
Negative 36.015.
Negative 36?
I must have did something.
That doesn't sound right. expect it to be 2.4 something. What's that? Yeah, it's sticking in my head, no, should get a positive number.
2.45.
2.45?
Does that sound right?
That sounds right. Was it a parentheses issue? Did you do this minus that divided by this and forget to do parentheses around the whole thing?
No, I put the whole thing in as it is.
2.45? That,
You got that, I still didn't get that.
what'd you get?
I got the same thing.
I got it twice.
What am I doing?
Alright, so this right here would be 29.4 minus, that should be 9.8 over 8,
That's right.
which should be 19.6 over 8.
Your minus is a negative sign, which means it's multiplying by negative 0.2.
Yeah, I got, 2.45.
Okay,
Let's
units?
use the operator version. I don't know.
Meters per second.
Like that, they're different.
Oh, meters per second squared.
Alright,
Crazy.
Is it 0.3?
alright, got it, resolved?
Yeah, I put a negative instead of a minus. I forgot that it does that.
I didn't know the TIs did that. Alright, good to know. Alright, so
That explains a lot.
this is not the answer. Because all we've done is check, is it going to move? So the question is it going to move? We plugged in the maximum static. Is the friction enough to keep it from moving? Is the static friction enough?
No,
Well, how can you tell?
because the friction is 1/3 of the force of the rope pulling the block.
Okay. And the other way, yeah. Conceptually, absolutely. Also, because
That number's
Oh.
bigger.
is what?
Basically,
It's bigger,
yeah.
so it's bigger than the static, it says.
Okay. It's also feeling confident we can pick the right direction of acceleration, and it's a positive number.
Yeah, that works too.
So we've established it is going to